Voltage drop is a crucial concept in electrical engineering, representing the decrease in electrical potential along a circuit. Understanding how to calculate voltage drop is essential for designing efficient and safe electrical systems. The basic formula for calculating voltage drop is voltage drop equals current multiplied by resistance. This formula, often written as volts equals amps times ohms, highlights the direct relationship between these three fundamental electrical quantities. Let's break down each component. Current, measured in amps, is the flow of electrical charge through a conductor. It represents the quantity of electrons passing a given point in a circuit per unit of time. The higher the current, the greater the number of electrons flowing, and consequently the greater the potential for voltage drop. Resistance, measured in ohms, is the opposition to the flow of current in a circuit. Every conductor possesses some degree of resistance, although good conductors like copper and aluminum have very low resistance values. Factors that influence resistance include the material of the conductor, its length, its cross-sectional area, and its temperature. Longer conductors have high resistance, while thicker conductors have lower resistance. Higher temperatures also generally increase resistance. Voltage drop, measured in volts, is the reduction in electrical potential energy as current flows through a resistance. It represents the amount of energy lost per unit of charge as electrons move through a resistive element. Voltage drop is an inevitable consequence of current flow in any real-world circuit. Now, let's delve deeper into how to apply the formula voltage drop equals current times resistance. To calculate voltage drop, you need to know both the current flowing through the circuit and the resistance of the component or conductor in question. Firstly, determine the current. The current can be determined by direct measurement using an ammeter, or it can be calculated using Ohm's law, which states that current equals voltage divided by resistance. If you know the voltage source and the total resistance of the circuit, you can calculate the current. Secondly, determine the resistance. The resistance of a component is typically specified by the manufacturer and can be found on the component's datasheet or labeling. For conductors, the resistance can be calculated using the formula resistance equals resistivity times length divided by area. Resistivity is a material property that indicates how strongly a material opposes the flow of current. Length is the length of the conductor, and area is the cross-sectional area of the conductor. This calculation is crucial for determining the appropriate wire gauge for an electrical installation. Thirdly, apply the formula. Once you know the current and the resistance, simply multiply them together to find the voltage drop. For example, if a circuit has a current of 10 amps flowing through a resistor with a resistance of 2 ohms, the voltage drop across the resistor would be 10 amps times 2 ohms, which equals 20 volts. It is important to note that voltage drop is cumulative. If a circuit has multiple resistive elements in series, the total voltage drop is the sum of the voltage drops across each individual element. This is because the current flows through each resistor sequentially, losing energy at each step. Understanding the factors that influence voltage drop is crucial for designing efficient electrical systems. Excessive voltage drop can lead to several problems, including reduced performance of electrical equipment, overheating of conductors, and increased energy consumption. Firstly, wire gauge selection. Choosing the correct wire gauge is paramount for minimizing voltage drop. Thicker wires have lower resistance, which reduces voltage drop. The National Electrical Code, or NEC, provides tables, such as NEC Table 310.15b16, that specify the ampacity of different wire gauges. Ampacity is the maximum current a conductor can carry without exceeding its temperature rating. It is important to select a wire gauge that not only has sufficient ampacity but also limits voltage drop to an acceptable level. Secondly, circuit length. Shorter circuits have lower resistance and therefore lower voltage drop. When designing electrical layouts, it is advisable to minimize the length of circuits as much as possible. This can be achieved by strategically locating electrical panels and equipment. Thirdly, load balancing. Unevenly distributed loads can cause excessive current flow in certain circuits, leading to increased voltage drop. Balancing the load across different circuits helps to ensure that current is distributed more evenly, reducing the overall voltage drop. Fourthly, conductor material. Copper and aluminum are the most common conductor materials used in electrical systems. Copper has a lower resistivity than aluminum, meaning that it has lower resistance for a given size. However, aluminum is lighter and less expensive than copper, making it a viable option for some applications. When using aluminum conductors, it is necessary to use larger wire gauges to achieve the same voltage drop performance as copper. Fifthly, temperature. The resistance of conductors increases with temperature. This means that voltage drop will be higher at higher temperatures. It is important to consider the operating temperature of conductors when designing electrical systems, especially in environments with high ambient temperatures. Sixthly, connections. Poorly made connections can introduce additional resistance into a circuit, increasing voltage drop. It is important to ensure that all connections are clean, tight, and properly made. Using appropriate connectors and termination techniques can help to minimize connection resistance. Voltage drop calculations are not only essential for design but also for troubleshooting electrical systems. If equipment is not performing as expected, excessive voltage drop could be the culprit. By measuring the voltage at different points in a circuit, you can identify areas where voltage drop is excessive. To measure voltage drop, use a voltmeter to measure the voltage at the source and at the load. The difference between these two voltages is the voltage drop. For example, if the voltage at the source is 120 volts and the voltage at the load is 115 volts, the voltage drop is 5 volts. Once you have identified an area of excessive voltage drop, you can investigate the cause. This may involve checking for loose connections, corroded conductors, or overloaded circuits. Correcting the underlying cause of the voltage drop will improve the performance and efficiency of the electrical system. In summary, the formula voltage drop equals current times resistance is a fundamental tool for electrical engineers and electricians. By understanding this formula and the factors that influence voltage drop, you can design and troubleshoot electrical systems effectively. Remember to choose the correct wire gauge, minimize circuit length, balance loads, use appropriate conductor materials, consider temperature effects, and ensure good connections. By following these guidelines, you can minimize voltage drop and ensure the safe and efficient operation of electrical equipment. Voltage drop calculations also play a critical role in ensuring compliance with electrical codes and standards. The NEC, for example, specifies maximum allowable voltage drops for different types of circuits. Exceeding these limits can result in code violations and potential safety hazards. It is essential to consult the relevant codes and standards when designing and installing electrical systems to ensure that voltage drop is within acceptable limits. Furthermore, specialized software tools are available to assist with voltage drop calculations. These tools can automate the process of calculating voltage drop in complex circuits, taking into account factors such as wire gauge, circuit length, load distribution, and temperature. Using these tools can save time and effort and improve the accuracy of voltage drop calculations. In addition to the basic formula, more advanced voltage drop calculations may be required for certain applications. For example, in alternating current or AC circuits, impedance, which is the AC equivalent of resistance, must be considered. Impedance includes both resistance and reactance, which is the opposition to current flow due to inductance and capacitance. The formula for voltage drop in AC circuits is voltage drop equals current times impedance. Calculating impedance requires a knowledge of AC circuit theory and the properties of inductors and capacitors. Also, nonlinear loads, such as electronic devices, can introduce harmonics into the electrical system. Harmonics are currents and voltages with frequencies that are multiples of the fundamental frequency, which is typically 60 Hz in the United States. Harmonics can increase voltage drop and cause other problems, such as overheating of equipment and interference with electronic devices. Mitigating harmonics may require the use of harmonic filters or other specialized equipment. When performing voltage drop calculations, it is important to consider the accuracy of the input data. The accuracy of the results depends on the accuracy of the current and resistance values used in the calculation. Inaccurate data can lead to incorrect conclusions and potentially unsafe designs. Use reliable measuring instruments and consult reputable sources for material properties and component specifications. Let's consider some practical examples of voltage drop calculations. Example 1 involves a simple residential circuit powering a lighting fixture. Suppose a 120-volt circuit with a 14-gauge copper wire is used to power a 100-watt light bulb located 50 feet from the electrical panel. The current drawn by the light bulb can be calculated using the formula power equals voltage times current, which gives current equals power divided by voltage. In this case, the current is 100 watts divided by 120 volts, which equals 0.83 amps. The resistance of the 14-gauge copper wire can be found in NEC Table 8. The resistance is approximately 2.525 ohms per 1000 feet. For a 50-foot run, the resistance is 50 feet divided by 1000 feet times 2.525 ohms, which equals 0.126 ohms. Since the circuit involves a round trip, the total wire length is 100 feet and the total resistance is 0.252 ohms. The voltage drop is therefore 0.83 amps times 0.252 ohms, which equals 0.21 volts. This voltage drop is relatively small and would not significantly affect the performance of the lighting fixture. Example 2 involves a longer commercial circuit powering a motor. Suppose a 480-volt circuit with a 4-gauge aluminum wire is used to power a 10-horsepower motor located 200 feet from the electrical panel. The full load current of the motor can be found in NEC Table 430.250. For a 10-horsepower, 480-volt motor, the full load current is approximately 14 amps. The resistance of the 4-gauge aluminum wire can be found in NEC Table 8. The resistance is approximately 0.797 ohms per 1000 feet. For a 200-foot run, the resistance is 200 feet divided by 1000 feet times 0.797 ohms, which equals 0.159 ohms. Since the circuit involves a round trip, the total wire length is 400 feet and the total resistance is 0.319 ohms. The voltage drop is therefore 14 amps times 0.319 ohms, which equals 4.47 volts. The percentage voltage drop is 4.47 volts divided by 480 volts times 100%, which equals 0.93%. This voltage drop is also relatively small and would not significantly affect the performance of the motor. However, if the motor were located further away from the panel, or if the wire gauge were smaller, the voltage drop could be excessive. Remember that voltage drop is an important consideration in electrical system design and troubleshooting. By understanding the formula and the factors that influence voltage drop, you can ensure the safe and efficient operation of electrical equipment. Remember to consult the relevant codes and standards when designing and installing electrical systems to ensure that voltage drop is within acceptable limits. Finally, remember to use reliable measuring instruments and consult reputable sources for material properties and component specifications. Voltage drop is not always constant. It can fluctuate depending on the load and the operating conditions of the electrical system. In circuits with variable loads, such as those powering motors or other dynamic equipment, the voltage drop will vary as the load changes. It is important to consider the maximum expected load when calculating voltage drop to ensure that the system can handle the worst-case scenario. Transient voltage drops can also occur during events such as motor starting or switch-in operations. These transient voltage drops can be more significant than the steady-state voltage drops and can cause equipment to malfunction or trip circuit breakers. Mitigating transient voltage drops may require the use of surge suppressors or other specialized equipment. In critical applications, such as hospitals or data centers, it is essential to maintain voltage drop within very tight limits to ensure the reliable operation of equipment. This may require the use of redundant power supplies or uninterruptible power supplies, or UPS systems to provide backup power in the event of a power outage. In addition to the factors already discussed, other factors can also influence voltage drop, such as the presence of harmonics, the type of load, and the grounding system. Harmonics can increase voltage drop and cause other problems, such as overheating of equipment and interference with electronic devices. Nonlinear loads, such as electronic devices, can generate harmonics. The grounding system can also affect voltage drop. A properly designed and installed grounding system can help to minimize voltage drop and improve the safety of the electrical system. A poor grounding system can increase voltage drop and create a shock hazard. It is important to ensure that the grounding system is properly installed and maintained. Regularly inspect the grounding system for corrosion, loose connections, and other problems. Also, consider the environmental conditions. In corrosive environments, such as those near the ocean or in industrial areas, conductors and connections can corrode over time, increasing resistance and voltage drop. In these environments, it is important to use corrosion-resistant materials and to regularly inspect and maintain the electrical system. Voltage drop is a complex phenomenon that is influenced by many factors. By understanding these factors and by following best practices for electrical system design and installation, you can minimize voltage drop and ensure the safe and efficient operation of electrical equipment. So, to reiterate, the formula voltage drop equals current times resistance is the basis for understanding this crucial electrical concept. The units of measurement are volts, amps, and ohms, respectively. Accurate calculation and careful consideration of influencing factors will lead to reliable and code-compliant electrical systems. Remember to consult the NEC and other relevant standards for specific requirements and guidance. Electrical safety is paramount. Always to energize circuits before working on them and follow proper safety procedures. If you are not qualified to work on electrical systems, consult a licensed electrician. By understanding voltage drop and by following proper safety procedures, you can ensure the safe and efficient operation of electrical equipment.